Okay, we are going to talk about our project for the Qiskit Hackathon Global. This is a new method for converting inequality constraints optimization problem into QAOA representations. Who talks is Alejandro Montañez and my partner Freya Shah. Okay.
So many optimization problems have inequality constraints in them that first need to be converted to equality constraints, which adds on various variables. And then these equality constraints further needs to be converted into binary representation to be solved by quadratic penalizations, which further adds new variables and it increases the number of qubits. So here we look at a different approach to reduce the number of qubits for the bin packing problem, which is an optimization problem that has inequality constraints, and we solve it using QAOA, which is the quadratic approximation optimization algorithm. So what basically the bin packing problem is that we are given a certain number of items with an assigned weight, and we are given the containers with the maximum weight, and we need to figure out a way in which we need to arrange these items into this container such that we utilize the minimum number of containers to store them. And as the number of items increase, it becomes an NP hard problem to solve for the classical computers.
Okay, our new approach consists on, well, we were thinking how we can change this usual method to convert these inequality constraints into equality ones and converting this into binary representation, but not adding all the qubits needed for that, because this increase a lot and we can lose into we cannot find the optimal point if we do this process, or at least we couldn't find that solution. But we are going to talk more about this after. But here we came to this approach when we thought that maybe an exponential function is a good representation. Here we have the negative of an exponential function. Then this, for a negative value, is going to be higher than for a positive one. And this is what we want. If the sum of the weights in each item is greater than the maximum weight that is allowed in this bin, when we have a greater penalization, that we have less weight in that bin. And yeah, this exponential function works well for that, but we cannot represent an exponential function in terms of q. We need at least to go to the quadratic form, or this is the maximum. Then we have to translate this into a representation into quadratic. Then we expand the exponential function, the negative of the exponential function, and we truncate this into the quadratic form. Then we have this function where t represents the the maximum weight allowed in the bin minus the sum of the weights in that bin. Then if we have a greater sum of the weights, then this is going to be a negative, and negative, then this is going to grow exponential. And here we have at the right this approximation in orange, and we have here how this, for a negative value of t, we have a greater penalization that if we have a positive value. And the exponential, well, at least for from going to -2 to 2 is close to our representation. Okay, and now we look at how we can reduce the number of qubits um, using the current approach that has the Qiskit optimization library from converting this problem. Then we look and for like after 4 items is going to be impossible to be solved by a simulator that we have in our computers or even in the CAS simulator. And with our new approach, we have like less number of qubits, and we can go even to 5 number of items.
Oh, so now comparing the solution from the classical method and our new approach. So here is the ideal solution, which is by the simplex solution, which we have considered as the optimal solution. And when we compare it with the classical QAOA converter, which is the classical method that we use right now, then it doesn't match the ideal solution. But with our new approach, it perfectly matches the ideal solution, and this is for 3 items, and uh, the maximum weight of the bean is 15. uh, and talking about the ratio of convergence for the two methods, we repeated the QAOA on the problem with 3 items, 3 bins, and maximum weight of 15 with 10 different initial conditions. And as we can see here on the graph, that the classical QAOA method like does not converges to the optimal solution, but the new QAOA method converges 100% of the time with the ideal solution.
Okay, and from that, like we saw that we couldn't solve these four with the classical approach, even for 3 items. Sometimes this converts, sometimes not. But for that case, that specific case didn't convert. And we like go from here just our with our classical approach, with our new approach. Then we are going from 3 items to 5 items and see what is the ratio of convergence. But because only reducing the number of qubits is not even something good if we cannot ensure that we can that our method is going to convert for more items. But what we see here, and we restrict the classical because this is an hybrid method when we use Covila as classical optimizer and we use QAOA as quantum optimizer. Then a combination of both for 3, 4, and 5 items with 5 different cases, which these different cases are like randomly selecting the weights in each case differently from the other. And we repeat this 10 times. Then we want to see how many times we have the optimal solution. We consider the optimal solution that give us the simplex optimizer and the classical solution. And then we replace the classical solution in terms of items and bins into the um, our new solution, and we find what is the optimal point. And for 3 items, we almost always find the optimal solution, restricting this to 10 iterations, the maximum number of iterations of the classical optimizer COVID lab, and 3 repetitions. And for 3 items and 4 items, we find like optimal solutions sometimes more frequently, but we find for 5 items this start to be more complicated, and we increase the number of iterations to 100, and with 4 repetitions for the QAOA, and we still find that sometimes this converge, but here we should have an we have to adjust the hyperparameters of the our solution mm, to try to improve the ratio of convergence. Well, and about the conclusion, we can say two things. Like the first, our approach is good to reduce the number of qubits used for solving these problems with inequality constraints. And the second thing is like we increase the ratio of convergence using this approach than what we have classically with the converter of the Qiskit library, the optimization library. And thank you.